Let's explain. On a TCP/IP network, data travels from one port on a sending computer to a port on the receiving computer. A port is an address that identifies the application associated with the data. The source port number identifies the application that sent the data, and the destination port number identifies the application that receives the data. Each port is assigned a unique 16-bit number in the range 0 through 65535. Additionally, there are two types of ports, TCP and UDP, that are based on their respective protocols. Today, the very existence of ports and their port numbers is more or less transparent to the users of the network. As many ports are standardized, thus a remote computer will know which port it should connect to for a specific service. For example, all servers that offer Telnet services do so on TCP port 23, and web servers normally run on TCP port 80. This means that when you dial up the internet to connect to a web server via the internet, you automatically connect to port 80, and when you use Telnet, you automatically connect to port 23. TCP/IP protocol uses a modifiable lookup table to determine the correct port for the data type. The following table lists some of the well-known port numbers for common protocols. UDP port number 15 NetStat, TCP port 21 FTP, TCP port 23 Telnet, TCP port 25 SMTP, UDP port 53 DNS, UDP port 69 TFTP, TCP port 70 Gopher, TCP port 79 Finger, TCP UDP port 80 HTTP, TCP port 110 POP3, UDP port 111 or PC, TCP port 119 NTP Network News Transfer Protocol, TCP port 123 NTP, UDP port 137 Net Bias Name Service, UDP port 161 Simple Network Management Protocol, Network Monitor, UDP port 2049 NFS. In multi-user systems, a program can define a port on the fly if more than one user requires access to the same service at the same time. Such a port is known as a dynamically allocated port and is assigned only when needed. For example, when two remote computers dial into a third computer and simultaneously request telnet services on that system. The combination of an IP address and a port number is known as a socket. A socket identifies a single network process in terms of the entire internet. Two sockets on the one sending system and one on the receiving host are needed to find a connection for connection-oriented protocols such as TCP. You may hear or see the terms sockets. Sorry, now you may hear or see the terms sockets and port used as if they were interchangeable terms, but they are not. Sockets were first developed as a part of the BSD Unix system kernel, in which they allow processes that are not running at the same time or on the same system to exchange information. You can read data from and write data to a socket just as you can do with a file. Socket pairs are bidirectional so that either process can send data to the other. Understanding IP addressing. As you know from the Internet Protocol section earlier in this chapter, IP moves data between computer systems in the form of a datagram, and each datagram is delivered to the destination port number that is contained in the datagram header. Destination port number or address is a standard 16-bit number that contains enough information to identify the receiving network and the specific host on that network for which the datagram is intended. In this section, you will learn what IP addresses are, why they are so necessary, and how they are used in TCP/IP networking. Ethernet addresses explained. You may remember from an earlier section that TCP/IP is independent of the underlying network hardware. If you are running on an Ethernet-based network, be careful not to confuse the Ethernet hardware address with the IP address required by TCP/IP. Each Ethernet network card has its own unique hardware address known as the Media Access Control MAC address. This hardware address is predefined and pre-programmed on the NIC by the manufacturer of the board as a unique 48-bit number. The first three parts of this address are called the Organizationally Unique Identifier (OUI) and are assigned by the Institute of Electrical and Electronic Engineers (IEEE). Manufacturers purchase OUIs in blocks and then assign the last three parts of the MAC address, making each assignment unique. Remember that the Ethernet address is predetermined and is hard-coded onto the NIC. IP addresses, however, are very different. IP addresses explained. TCP/IP requires that each computer on a TCP/IP network have its own unique IP address. There are two addressing schemes for TCP/IP, IP version 4 and IP version 6. You should know how each of these schemes differ. Sorry, now just bear with me here. IP version 4. An IP version 4 address is a 32-bit number usually represented as a four-part number, with each of the four parts separated by a period or decimal point. You may also hear this method of representation called dotted decimal or quad decimal. In the IP version 4 address, each individual byte or octet, at as it is sometimes called, can have a value in the range of 0 through 255. The way these addresses are used varies according to the class of the network. So all you can say with certainty is that the 32-bit IP version 4 address is divided in some way to create an address for the network and an address for each host. In general, though, the higher ordered bits of the address make up the network part of the address, and the rest constitutes the host part of the address. In addition, the host part of the address can be divided further to allow for a sub-network address. Some host addresses are reserved for special use. For example, in all network addresses, host numbers 0 and 255 are reserved. An IP version host address with all host bits set to 0 identifies the network itself, so 52.0.0.0 refers to network 52. An IP address with all host bits set to 255 is known as a broadcast address. The broadcast address for 204.176 is 204.176.255.255. A datagram sent to this address is automatically sent to every individual host on the 204.176 network. ARN assigns and regulates IP addresses on the internet. You can get one directly from ARN, or you can ask your internet service provider (ISP) to secure an IP address on your behalf. Another strategy is to obtain your address from ARN and only use it internally until you are ready to connect to the internet. IP version 6. IP version 6 was originally designed because the number of available IP version 4 addresses was running low. Because IP version 6 uses a 128-bit addressing scheme, it has more than 79 octillion, and that's 79 dot all the zeros there, to you and me, times as many available IP addresses as IP version 4. Also, instead of using binary digits and decimal digits, IP version 6 uses 8 sets of 4 hexadecimal digits, like so: 3 FFE colon 0B double zero colon 0800 colon 0002 0000 colon 0000 colon 0000 colon 000C. In addition, you can abbreviate these very long addresses by dropping leading zeros, like the zero before B in 0B00. You can also drop any single grouping of 0 octets as in the number above between numbers, as long as you can replace them with a double colon and they are complete octets. You can't drop 3 zeros in the second octet to make it just B instead of 0B00, for example. If you applied this rule, known as the zero compensation rule, to the above address, it would make the example address look like so: 3FFE colon 0B00 colon 0800 colon 0002 colon 000C. As with IP version 4, there are several addresses that are reserved for special use. The IP address :/0 is the default address for hosts like 0.0.0.0 in IP version 4. The address :1/128 is reserved for the local loopback, like 127.0.0.1 in IP version 4. IP version 6 also includes the provisions for the old IP version 4 hosts so that they can be migrated to the new addressing scheme. This is accomplished by using the address :xxx.xxx.xxx.xxx, where the last 4 sets of digits refer to the old IP version 4 address. IP version 4 address. The way a host is configured is one very unique aspect of the IP version 6 addressing scheme. Instead of an IP address, subnet mask, and default gateway, each station is required to have 3 different addresses. First of all, The host has an address for each upstream supplier, a local address and a linked local address. The local address is a number like :1/128 that defines the local host. The linked local address is the address for the local subnet. Finally, IP version 6 has some other unique addressing concepts like auto configuration similar to DHCP but extended further, and neighborhood discovery, whereby the IP version 6 host discovers its network surroundings. IP version 4 address classifications. In the 32-bit IP address, the number of bits used to identify the network and the host vary according to the network class of the address. If you never connect your intranet to the outside world and the internet, you have no need to concern yourself with this information. If you plan to connect to the internet and to do well on the exam, you need to know that several classes are as follows. Class A is used for very large networks only. The high order bit in a Class A network is always 0, which leaves 7 bits available to define 1 to 127 networks. The remaining 24 bits of the address allow each Class A network to hold as many as 16.777.214 hosts. Example of Class A networks include General Electric, IBM, Hewlett-Packard, Apple, Xerox, DEC, Columbia University, and MIT. All possible Class A IBM networks are in use, no more are available. Class B is used for medium-sized networks. The two high-order bits are always tens, that's 1, 0, not 10, and the remaining bits are defined to 16,384 networks, each with as many as 65,534 hosts attached. Examples of Class B networks include Microsoft and Exxon. All Class B networks are in use, no more of them are available. Class C is for smaller networks. The three high-order bits are always 110 and the remaining bits are used to define 2-097-152 networks, but each network can have a maximum of only 254 hosts. Class C networks are still available. Class D is a special multicast address and cannot be used for networks. Four high order bits are always 1110 and the remaining 28 bits allow access to more than 268 million possible addresses. Class E is reserved for experimental purposes. The first 4 bits in the address are always 1111. Because the bits used to identify the Class A are combined with bits that define the network address, we can draw the following conclusions from the size of the first octet or byte of the address. A value of 126 or less indicates a Class A address. The first octet is the network number, the next three the host address. A value of exactly 127 is reserved as a loopback test address. If you send a message to 127.0.0.1, the ping doesn't actually generate any network traffic. It does, however, test that TCP/IP is installed correctly. Using this number as a special test address has unfortunate effect of wasting time. More than 24 million possible IP addresses. A value of 128 through 191 is a Class B address. The first two octets are the network number and the last two are the host address. A value of 192 through 223 is a Class C address. The first three octets are the network address and the last octet is the host address. A value greater than 223 indicates a reserved address. So I'm going to leave it here today for this video. I hope you liked it. If you did, please consider sharing and subscribing, and thank you again.